Section 25.1, the nucleus. The two objectives here are to identify some of the properties of the nucleus and to explain why some nuclei are unstable. First, we'll talk about what's in the nucleus. And what's in the nucleus are called nucleons. And these are those subatomic particles of protons and neutrons. Remembering that the electrons are not in the nucleus but outside of the nucleus. So, what we're going to do is talk about three different things. First, you have something called a mass number. And the mass number is the total mass of the nucleus. Well, since the protons and neutrons have an approximate mass of 1 atomic mass unit, we could say that it's just the number of nucleons total, protons and neutrons. But the atomic number is represented by the number of protons in the nucleus. So that's what's given here. So aluminum, for example, has 13 protons in its nucleus, so its atomic number is 13. But the total mass is 27. So that means that the neutrons must be 14, because 13 plus 14 gives me 27. So what we can say here is that the mass number, A, is always equal to the atomic number, Z, plus the number of neutrons, N. Now let's look at the number of protons versus neutrons. So in each element, there's a specific number of protons, which gives it its atomic number, as we said a minute ago. But the amount of neutrons in it can vary. And if there's a change in the amount of neutrons in an element, you would say that it's an isotope of that element. For example, like carbon-12 and carbon-16. So carbon has 6 protons, but it can also have 6 neutrons. Carbon has 6 protons, but it can have 8 neutrons. And there's actually, I think, over like 10 or 15 isotopes of carbon. So what this means here is that this one, this is going to be your 6 protons in here, and they're not packed this way. But there's also 6 neutrons. Oops, and there's 6. But in this element, although there's 6 protons, there's an extra 2 neutrons here when compared to the original one. Now, what you see on a periodic table, though, is not an exact integer value for the mass. You'll see this. You'll see carbon 6 and then 12.001. And the reasoning is this. If you took all the carbon isotopes that exist as elements in their percentage of them that exist on the Earth, for example, out of all the carbon isotopes, maybe 80 of them are carbon-612. So you take 80%, not 80 of them. So you take 80% times this mass number plus, say, if 10% of them exist this way, 10% times this mass number, and you keep going through this process, and you can do what's called a weighted average. So this is if you took all the carbon elements that exist, added all their masses up, and divided by however many there are, this would be the overall weight, or mass, rather, mass of the carbon elements on Earth. Let's take a look next at the density of a nucleus. So first, we have to know that nuclei are approximately spherical. When all of those atoms are packed together, the nucleus is approximately spherical. And the volume of the nucleus is proportional to the total number of nucleons, the mass. And that makes sense if we think about it. Think about the volume and the mass and how they're proportional to each other. If I had an element like carbon, like before I was showing, it'd have 6 protons and 6 neutrons. And these are not the way it would be arranged. I'm just drawing them anyway. And if I had another element like magnesium, which is 1224, it's about double the amount of mass here, right? So it'd be 12 protons. 12 neutrons. And what we'll notice here is that we have two different elements. One is much smaller in mass, or it's half the mass of the mass here. And what we will notice is that the volume of this approximately doubles as well. So the volume doubles, and the mass also doubles. Now, what that means is this, and this is the really interesting part about the density. The density of nuclei in general are pretty much all the same. Because remember that density, which is rho, R-H-O in physics, it's like a little lowercase p, but you start from the bottom with that loop. Okay, loop it like this. So what we know, that means that the density is mass over volume. So if I go from carbon to magnesium, I'm doubling the mass, right? Because I have double the amount of nucleons, but I'm also doubling the volume, because the volume is proportional to the total number of nucleons. So what happens is if these both double, I still end up with the exact same density. So what we can say again is that all nuclei have approximately the same density. What is that density? Well, that density is an extremely large number. The density of nuclei is 2.3 times 10 to the 17 kilograms per cubic meter. Now, to give you a sense of the significance of that number, that's around 230 trillion times more dense than water. So if you held, say, a bucket of water in your hand, and it was like 2 pounds. Well, if that was a bucket of nuclei, which is not possible, but if you could have nuclei all in there, it would be 230 trillion times more heavy to carry. That's how dense a nucleus is. Well, don't forget that the reason that an atom itself, or why we're not that dense, is because we're mainly made up of empty space. The nucleus is very, very dense, but a lot of that atom is empty space between the electrons and the nucleus, and between the electron orbits. So as a result, our bodies or elements around us are not as dense as a nucleus would be because of that empty space. Finally, we'll talk about nuclear stability. We have to think about this for a second. We haven't really honed in on the nucleus and said to ourselves, well, if a nucleus is made up of all these protons and these neutrons, okay, all like they're not in rings, but they're just randomly assorted in this sense for now. So say I've got protons and neutrons, right? Well, the majority of these charges are or half of these charges around are positive, and then the other ones are neutral. So again, the red ones, the neutrons, are neutral, but all those black ones have a positive charge. Well, two positive electric charges want to repel each other. So what keeps this nucleus together? Because the neutrons, well, they're neutral, so they're not helping really. They're just kind of hanging out there. Well, what happens really is that there's something called the nuclear force, also known as the strong force. This is one of our 4 fundamental forces. We've learned about gravitational force and electromagnetic force. Now we're going to be looking at the strong force. The strong force is responsible for holding the positive nucleus together. It exists between neutrons and protons, and protons and protons as well. So this is a charge, or not a charge, a force that exists between the nucleons inside of a nucleus. Now, the interesting thing is this. It's independent of charge, but it has to be at a short distance. So, for example, there's a strong force interacting between these two, between these two, between these two, between these two, maybe these two. But the minute we're looking at a strong force, there is no strong force between these two. It's too far apart. So it needs to be below a distance of 10 to the negative 15 meters. So we're talking at really, really, really close proximities. So what happens is this. This is the real interesting part. For heavy nuclei, right, for big nuclei, it's difficult for it to be stable. The reason that is, if you get bigger and bigger nuclei, these elements across from each other are not going to have a strong force. But since they're both protons, or like say these two, because these were neutrons, say this proton and this proton, there's no strong force holding them together, but there is an electric force that's pushing them apart. Okay, there is a force pushing them apart. So as the nucleus gets larger and larger and larger, the electric force is still there between a lot of the protons, but the strong force is not there between nucleons that are at a long distance. So the strong force doesn't continue to increase at the same rate as the electric force of repulsion. So once that electric force increases beyond the strong force, then the nucleus wants to break apart. You get things like natural radioactive decay. Okay, so what we say is, for heavy nuclei, you really need more neutrons than protons to maintain stability. Because if I load this thing up with neutrons, right? Keep loading this with neutrons. Well, neutrons have no electric force of repulsion, but neutrons do create the strong force. So more neutrons, more strong force, and while at that point, there's no electric force of increase. So I'm increasing the strong force, and the electric force is remaining constant. Let's put a, I'm not going to put a, let's put a 0 there to remain constant. It's not going up or down. Okay, so the electric force is constant while the strong force is going up because I have more and more neutrons there to create more and more of the strong force.